Hi, everyone. Welcome to the third lecture in this practical introduction to quantum computing. And I would like to start again saying thank you to you all. As you know, the two videos for the first two lectures are already available both on the CERN document server and on YouTube, and they have several thousand views both. So, well, we are really happy that you are interested in the course, you are following the lectures, and we also want to say thank you for all your feedback. We've received some questions, and as always, I will address them before we start with the content for today. So there were some people who let us know that there were some problems with the video for the first lecture. I've been told that this has been already solved, so sorry for the inconvenience. But the problem was apparently related to some browsers. So it was okay on some browsers, and it had some problems on others. So if this happens again, please let us know. But also you can try to switch your browser, and maybe with a different one it will work while we solve the problem if it happens again. We also received some questions regarding the physical implementation of qubits. As you know, this is something that we are not covering in the course, but I can point you to some useful resources. So in the book by Janowski and Manucci, there is a very short chapter, which is an introduction to different technologies that can be used to construct, to build quantum bits. And if you only want to have a general knowledge of the different techniques and the main advantages of ones and others, this is a very short, very nice introduction. If you want more details, then you have whole chapters, longer chapters, in both the book by Siegelman and the book by Nielsen and Chuang. They are all in the recommended books list. And I have also included a link to an online course with video lectures and some additional material in the list. So this is an update that I have published both in the first and second lectures, the pages in Indico, and also in this third, and the page for this third lecture. So you can just take a look at the chapter in Janowski and Manucci's book, which is short, or if you want more details, you can refer to the books by Siegelman and by Nielsen and Chuang, or you can try to follow this course, which I think is also very interesting. Okay, so I think those are the most popular or the most frequent questions this week. The other ones I have tried to solve by replying to the emails, and I think I have answered to all the questions related to the content of the course. So please feel free to send your feedback or your questions, and of course the people which are joining us in the Zoom call, please feel free to ask questions at any time. Okay. So I would like to start today by going back to the notebook that we were using last time. Okay, I think you should be seeing it now on your screens, because we didn't have time to wait for the circuit to be run on the computer. I want to show you the results, but I also want to show you some information that you can get about the devices in which you can run your circuits, that I think is very interesting and can help you decide which computer is the most appropriate for your experiments, and it can help you also understand a little bit better why how these quantum computers work. Okay, so for instance, with this command here, backend overview, you have this nice list view of the different devices. Probably you will have some other different ones, but you will have some in common with this list here. And the information includes the number of qubits, the number of pending jobs, whether this is the least busy device at the moment or not, and two figures of merit that are quite interesting and quite important. These are the times T1 and T2. And roughly speaking, you have more information in the books in the recommended list. Roughly speaking, T1 is related to the time that a qubit, which is in state 1, lasts in that state before decaying to 0. So the thing here is that state 1 is more energetic than state 0. So eventually, this state decays back to 0. Okay, so if we have a qubit which initially is in state 0 and we apply the X gate, it will go to state 1, but eventually it will decay to 0. Okay, so this time is related to the probability of still finding the qubit in state 1 once that we have applied the X gate to a qubit in state 0. Okay, so this is an interesting figure of merit, and of course, the higher this time, the better is the device. Okay, here we see the average value over all the qubits in the device, but this time is different for each qubit in the computer. Okay, and then we have the time T2, which is related to the probability of finding a qubit that we have set in superposition is still in that superposition. So here we start with a qubit in state 0. We apply for instance, the H gate, and we obtain the plus state, an equal superposition of 0 and 1. And this time is related to the probability of when measuring or when doing some transformations on this qubit, that it still is in this superposition and it doesn't decay or collapse to 0 or 1. Okay, so again, the higher this time, the better your results will be, because the more quantum is the behavior of the qubits. Okay, so this is information that you can obtain with this command, backend overview. And if you want more information about a particular device, you can use this other command, backend monitor. Okay, with the name of the device that you want to get information from. In this case, I am checking the properties of the device that is called Ourense. Okay, so here again you have information, but now this is specified qubit by qubit. This device has 5 qubits, and you see here some of the information related to the frequencies at which these qubits operate. This is something that is related to the physical implementation. And then you have information about the T1 and T2 times again. And you also have here information about the errors of the different gates. Okay, so these are 1 qubit gates, and you see here that you have an error that can occur when you apply these gates. Okay, so these are for the U2, U3 gates, which are similar to the rotations that we have been studying. Also here you have information about the multi-qubit gates. In this case, the C0 gates, the 2 qubit gates that we studied last week. And you see here the error of these gates, which is generally 1 order of magnitude higher than the error for the 1 qubit gates. Okay, so when we try to operate with a couple of qubits to entangle them, this is more difficult and the error is a bit higher. Okay, so this is something that you can take into account when you are designing your circuit. You also see that the different gates between the different qubits. Here we have, for instance, the C0 between 0 and 1, the C0 between 1 and 2. The different C0 gates have different errors. So maybe you want to select the qubits in which you want to operate according to these errors. Okay. Also, something that is interesting is that not all pairs of qubits can be entangled or directly, or can be or we can apply a CNOT gate to them. Okay, so here you see that we have a CNOT gate between 0 and 1, between 1 and 2, between 1 and 3. But for instance, we have not CNOT gate between 0 and 4. Okay, so this is something that we can also see in the information that is given here with what is called the coupling map. The coupling map gives us the connections between pairs of qubits in which we have the possibility of applying a CNOT gate. Okay, this is something that you can also check. Let me see if I can switch the tab. Sorry. Okay, so this is something that you can also see here. If you click, for instance, on IBM-Q Ourense, you see this diagram, this graph, in which you have the different qubits and the connections between them, the pairs of qubits in which we can apply a CNOT gate. We also have a color code for the errors of the gates. So the qubit is encircled in this color, which when it's closer to purple is has more error. When it is closer to this green color, has less error for the 1 qubit gates. And then the arrows between the 2 qubits, which can be connected with a CNOT, again has this color code. Okay, so closer to purple, more error; closer to green, lesser. Okay, so there is a question here by R. Bianchi about the T1 and T2 times that I was explaining. So I will read it. Is it possible that states decay during a calculation? If yes, are we warned by the machine system in any way? Well, the answer is that, of course, the states can decay, can lose their quantum properties during the computation. You see here that the times that we are seeing, for instance, for Ourense, are in the range of microseconds. So this is the time that these qubits more or less maintain their quantum properties. The time of operation of a gate is typically around several dozens nanoseconds. Okay, so you have time to theoretically to apply maybe 100, 200, several hundred operations, gates. But after that, you are not guaranteed to have something that is still quantum, okay? And it can happen, of course, it can happen before that. And you are not warned because there is no way of checking this. Of course, you can perform some experiments and try to see whether the results you obtain for circuits in which you know the answer are correct. But in a given calculation, this is something that you cannot know, okay? That is why we, of course, need to apply as much as possible error correction, error mitigation. We will talk about this in the 7th lecture of the course, in the last lecture. And also this is why we repeat the experiment several times, because there is no guarantee that running it once will give you the correct answer. There can be errors, the qubits can lose their coherence or can decay, or something can happen and you obtain an incorrect result, okay? So I hope this answers the question. Okay, so if not, please let me know. Okay, so another thing that I wanted to show you are the results of the experiment. Remember that what we were doing here was running a circuit which prepared an entangled state, a Bell pair, okay, in which we know theoretically that the correlation between the measurement of the first and the second qubit is perfect, okay? So when we run this on the simulator, we always obtain 0, 0 or 1, 1. It is impossible to obtain different values in the qubits, okay, when we measure. However, when we run this on the actual device, in Ourense, for instance, in this case, maybe in your experiment, another different device was selected. But you see that there are some small probabilities of obtaining results that are not what we expected, are not 0, 0, or 1, 1. Of course, this can happen because the actual devices, the physical computers that we are using are not perfect, are subject to these errors. This is what the T1, T2, and the errors of the gates are about. Also the errors of the measurements. So this can happen, okay? But you see here that the probability is quite low, and the actual results fit the theoretical expectation quite well, okay? So you see here that for the device in blue, we obtain almost 50%, well, a little bit less than the 50% that we expected, but this is quite close, okay? So this is something that, that you should take into account. And when you run an actual experiment or a computation, this is something that you need to be prepared for, and you need to do some kind of statistical analysis or error correction, error mitigation in order to obtain correct answers. Okay? Okay, so with this explained, I would like now to go back to the slides and start talking about a very interesting experiment that uses entanglement to check whether reality is quantum or classical. Okay, so I'm starting in slide number 59. This is something that confused some people last week. So I'm always publishing all the slides from the beginning and adding new ones, okay? Just in case I need to go back for reference for some of the things that we have already covered. So please go to slide number 59, okay? And this experiment or this protocol or this game that we are going to study follows from the seminal work of John Bell. I told you about John Bell, who was a scientist here, a researcher here at CERN last week. And he, in 1964, published a paper in which he studied the property of entanglement of quantum systems. And he showed that if we only take into account classical explanations, what are called local hidden variable theories, then these correlations cannot be fully explained. I mean, if we consider an entanglement pair, there will be correlations in the measurements that are higher than what we expect if nature follows a classical local hidden variable theory. Okay, so this was a very interesting work that was not fully appreciated at the beginning, but then people began to realize that it was something really, really intriguing and really, really interesting. And what we are going to see here is a formulation based on this work, which was done in 1969 by Closer, Horn, Shimoni, and Holt. This is why we call this the CH-SH game, in which this theorem and these inequalities that John Bell developed in his seminal paper are transformed into a kind of game that will have different outcomes if we have a physical theory that allows these quantum correlations, and if we have a physical theory that is only classical. Okay, so again, we have Alice and Bob, which we know already from the BB-884 protocol, and we will meet them again in several other different contexts. And this time they are far apart, and they are participating in this game in which there is a referee that sends them bits X and Y. So in each round of the game, Alice receives a bit X, which can be 0 or 1, and Bob receives a bit Y, which again can be 0 and 1. And these bits are chosen, and this is very important, completely at random, uniformly at random. Okay, at each round they receive a bit, and this is completely random. The probability of obtaining 0 is 0.5, and the probability of obtaining 1 is again 0.5. Okay, and when they receive these bits, Alice and Bob have to reply with their own bits. They have to reply to the referee with a 0 or a 1. I'm going to call the reply, the bit chosen by Alice, A, and the bit chosen by Bob, B. Okay, and they win the round of the game if this formula here is satisfied. Okay, so this is a certain correlation or certain relationship that has to be verified by the bits sent by the referee and the bits chosen by Alice and Bob, which is related to these inequalities developed by John Bell. Okay, so for us, the important thing here is that since x and y can be either 0 or 1, notice that if either sorry, if either x is 0 or y is 0, then x times y is 0, and then the XOR of the bits chosen by A and B, by Alice and Bob, have to be also 0. This means that when either x is 0 or y is 0, Alice and Bob have to choose bits that are the same, that are equal, in order to win. Okay, but if x is 1 and y is 1, then in order to win the round of the game, Alice and Bob have to choose bits that are different. Okay, Alice can choose 0 and Bob can choose 1, and they win. Or Alice can choose 1 and Bob can choose 0, and they also win. Okay, and it's also important that they are far apart, so they cannot communicate. They are so far apart that there is no time in the interval that they have to respond, to reply to the referee, to communicate, because they are far apart, and communication is no faster than the speed of light. And then they cannot tell each other, well, I have received a 0, then let's choose whatever pair of bits will make us win. Okay, so this is a decision that Alice has to take on her own. Bob has to take on her own. What they can do is to decide to agree on a strategy beforehand. So before playing the game, they can agree that they are always going to answer 0, or they are always to answer the same as the bit that they receive, or that they are going to flip a coin at the moment, and then they are going to choose whatever the coin says. If it is heads, they reply with 0. If it is tails, they reply with 1, or whatever any other strategy they can conceive, but they cannot communicate during the game. Okay, so this is the setting of the game, and we want to study what is the probability that they can win a given round. Or if you want to see it in another way, what is the average number of rounds that they will win if they have the best possible strategy in the classical setting. Okay, with no quantum information, but with this joint strategy, and probably also the possibility of resorting to probabilistic bits or something like that. Okay, so it's easy to see that, well, there is this simple strategy, which is that Alice and Bob always reply 0, and then they win 75% of the times. Three out of 4 times they will win, because if either x is 0 or y is 0, then A and B must be equal. And if they always respond with 0, of course, their bits are equal. And since the referee is choosing x and y uniformly at random, the probability of choosing at least one 0, the probability of at least X being 0 or Y being 0 is of course 75%, okay? And if you study the possible classical strategies a little bit further, you realize that there is nothing better that they can do. Here we can see a table with the different possible deterministic strategies, classical strategies that they can follow. The legend here is that, well, for instance, for Alice, the reply can always be 0, or can always be 1, or can always be the bit that she receives from the referee, or the opposite of the bit that she receives from the referee. And for Bob, the choices are the same, okay? And here in the intersection of rows and columns, you see the probability of winning with those strategies. And then you can easily see that any strategy that uses a combination of these classical strategies, for instance, if you resort on flipping coins, or in changing the strategy every so many rounds or whatever, this will be a combination, a convex combination of these strategies, and then the probability of winning cannot be higher than the best of these strategies, okay? So it's easy to see that classically they can win at most 75% of the time. Now we change the setting a little bit, and we let Alice and Bob share not only classical information beforehand, so this strategy that they agreed upon, but also quantum information. In particular, we allow them to create entangled pairs of qubits, Bell pairs, and to keep one part of the qubit for the game, each of them. Okay, so they create a number of entangled pairs. We know how to do this. We already know how to do this with a quantum computer, and there are other physical processes that can produce these entangled pairs. For instance, what is called spontaneous parametric down conversion. There are several different ways. So they create these entangled pairs. They keep part of the pair for the game. Alice has one part of the pair, and Bell and Bob has the other part. And then they follow this strategy. They are going to measure the qubit, but depending on the bit that they receive from the referee, they sometimes are going to apply a certain rotation. Okay, so in particular, if Alice receives a 0, she measures her qubit and outputs the result. She does not apply any gate, so she has her part of the pair. She measures this part, and she obtains either a 0 or 1, and this is the qubit that she sends to the referee, back to the referee. But if she receives a 1, she applies this rotation around the y-axis with angle pi/2. And then she measures and replies to the referee with the result that she obtains. For Bob, it's similar, but if he receives a 0, then he applies this rotation with angle pi/4. And if he receives a 1, he applies the rotation with angle minus pi/4. And then he measures the qubit and sends back the result to the referee. Okay? And surprisingly enough, it can be shown that then their probability of winning is exactly the cosine square of pi/8, which is approximately 0.85, which is, of course, much bigger than 0.75 that you can obtain with the classical setting. Okay, this is something that you can check. This is an easy exercise. You can just write down the states that they obtain before measuring for each of the 4 different possibilities when they receive 0, 0, 0, 1, 1, 0, 1, 1, and then you can check the probability of obtaining pairs of bits that make them win the game. But there is an easier way that I want to show you of computing these probabilities with Quirk. Okay, so let me change the screen to my browser in which I have Quirk. Let me find it. Here it is. Okay, where is it? Sorry. Okay. You should be seeing now Quirk on my screen. So what we are going to do is to create first this entangled pair. Okay. Oh, sorry. This should be H. Okay. So now we have an entangled pair. You see here that we have 0, 0 with amplitude 1 over the square root of 2, 1, 1 with amplitude 1 over the square root of 2. So this is exactly the bell pair that we need. And now let's imagine that they both receive 0 from the referee. Okay, so the X is 0, Y is 0. So they should reply with bits that are exactly equal. Okay. In this case, what is Alice going to do? Alice is going to directly measure her qubit, but Bob is going to apply a rotation of pi over 4. Okay, so now if we check here the probabilities of obtaining 0, 0 and 1, 1, which are the winning results in this case, you see that we have 42.7, 42.7, which together make close to this 85% that I was telling you about, which is of course greater than 75%. Okay. Another situation is when Alice receives a 1, and then she applies this rotation of pi over 2. Okay, and then you see that the probabilities are again the same. Okay, in this case, they should reply with bits that are equal because Bob is still receiving a 0. Okay, let's see now what happens if Alice receives a 0, Bob receives a 1. In this case, Bob is applying a rotation of minus pi over 4, and again the probabilities of winning are around 85%. And the final case is when both receive a 1, and in this case, notice that Alice is applying this rotation of pi over 2, Bob is applying a rotation of minus pi over 4, and now they should reply with bits that are different. So the winning possibilities are 0, 1 or 1, 0. But again, the sum of the probabilities of 0, 1 and 1, 0 is around 85%. Okay, so this is something that it's not possible with classical local hidden variables theories, but it's possible with quantum entanglement. Okay, I'm going to go back to the slides. Okay, and this is something that it's very, very interesting because it gives us a possibility of testing in real life whether the predictions of quantum computing, or I mean of quantum mechanics, are real and are something that is different from what we expect if we only have classical correlations. Okay, and this is something that has been done. It was done already back in the 80s. There were some previous experiments, but they were not so convincing, or there were some problems or some interpretation problems. One of the most famous experiments using this kind of correlation was conducted by Alan Aspect and his team in 1981-82. And this diagram that we have here is the diagram of the experiment. This S here is a source of entangled pairs. This can be done, for instance, with photons, with this spontaneous parametric down conversion. And here we have A and B, which are polarizers that can be changed. The angle of this polarization can be changed according to the different angles that Alice and Bob have to apply. And then we have detectors for one polarization or the other. And this was conducted experimentally, and it agreed with the predictions of quantum theory, not with the predictions of local hidden variables, okay? There were some doubts about the methodology of these experiments and the following, because it could be conceived that there were some problems that could prevent this from being completely quantum, completely unlike classical, in the sense that, for instance, if the polarizers or the detectors were too close to each other, you could argue that maybe there is time for these detectors to send some kind of signal to the other, so the other can change their response somehow and make these correlations higher than they should be, okay? Or also, there was this loophole that had to be closed related to the detection efficiency of the experiment, in which not all the photons were completely detected. And then you could argue that, well, those photons that you did not measure were exactly the ones that were not correlated as quantum theory predicted, okay? So in 2005, Henson and his collaborators conducted this other experiment in which these loopholes of locality and detection were all solved at the same time. And again, the results were in complete agreement with quantum theory, okay? Another interesting thing is that it can be proved that this probability of 85%, more or less, is the maximum that you can obtain with any quantum strategy. If you try to do something more complicated with more qubits or different state, with more terms, with other kind of entanglement, well, there is nothing that you can do which is better than this. This is called Zirelson's bound. But there are other experiments in which you can obtain 100% correlation between the results, or 100% probability of winning the game. Okay, so this is another different game, also based on this kind of Bell inequalities, which was introduced by Greenberg, Horn, and Seilinger. So this is called the GHZ game. And in this case, we have three participants. We have Alice and Bob, and we also have Charlie. And they receive, each of them, a bid from a referee, but the referee now selects the bids from these strings. He cannot select any bid for any person, but he has to select at random from these four strings that, as you can see, have parity 0. Okay, so the number of ones is always even. And they win if this relationship holds between the bits that they respond and the bits that they have received. Again, you can prove that they can win, classically, they can win only with 75% of probability. But if they share this state here, which is again an entangled state, and they apply the Hadamard gate to their qubit, if they receive 1, they do not apply anything if they receive 0, and they then measure and return the answer, then they win 100% of the time. This is something that you can check. It's an easy exercise. You just consider the 4 different possibilities. You apply the H gates, or you leave the qubits unchanged, depending on what each person receives, and you compute the probability. And this is something that you can easily check, and they win 100% of the time. This is the reason why some people call this quantum pseudo telepathy, in the sense that it seems that Alice, Bob, and Charlie are reading each other's minds and know what they are going to send to the referee, and then they somehow agree and they can win 100% of the time. But this is not magic. This is not telepathy. This is just quantum entanglement at work. Okay. So this may seem like, well, a nice experiment, something that is really very interesting for the foundations of quantum theory, but it seems that it's not really very practical. Well, in fact, this is something that has been used and is being used in the last few years with a practical application, which is the production of randomness of real random bits, which can be certified. Okay, this is something that you can do because if you use this idea of the CHSH game or the GHZ game, you can see that if you win the game more than the 75% of the time that is predicted by classical theory, then there is something random happening in your measurements, okay, in your process. So this is something that cannot be deterministic. And if you apply these ideas with in combination with the theory of randomness extraction and some other very interesting ideas, you can use these to produce random bits that can be certified to be perfectly uniform, perfectly random. Okay, so this is something that, for instance, quantum computing companies such as Cambridge Quantum Computing are doing. We are collaborating with Cambridge Quantum Computing in trying to see what these protocols and these random bits can do, for instance, for Monte Carlo simulations. And I think this is a very, very beautiful theory and a very, very interesting topic of research. Okay, so I don't know if there are questions about this. Okay, so then what I'm going to do is to show you how to implement this CHSH game on the IBM Quantum Experience. And we are going to run an experiment which I think it's really very exciting, which is trying to see whether, okay, I have it here. Whether these quantum computers that we are using at the IBM Quantum Experience are really quantum or not, or if you want to see it in another way, whether nature is really quantum or not. So we are going to run this game, and we are going to see what is the probability of winning that we obtain. Of course, this is not a serious experiment in the sense that we can conclude with this that nature is really quantum, because there are several loopholes that we are not addressing here. Of course, the qubits that we are using are close together, so there is no separation between them, and you could argue that there is some kind of signal sent from one to the other. Also, I'm not going to generate the rounds of the game completely at random, so you could argue that maybe the quantum device somehow knows that I'm first running only with 0, 0, then with 0, 1, and then it responds accordingly. But well, of course, this is something that is not completely rigorous, but I think it's very interesting because it shows that you can do physics with one of these computers, or at least simulate one of these experiments from your home, just sending these programs to these quantum devices. And I think this is really something very exciting. Okay, so what we are going to do here is to create circuits that are going to depend on the X and Y bits that Alice and Bob receive. And then here I'm also introducing these parameters, which are the angles of rotation that they are going to use. Okay, so this is something that is not needed. I could just fix the rotations to the ones that we know that obtain the best possible probability of winning. But this is something that you can use in order to change a little bit these angles and see that you obtain different results, and that you do not obtain something that is better than this 85% probability of winning. Okay, so what I do here first is to create the bell pair. We already know how to do this. And then for Alice, depending on whether she receives a 0 or a 1, I apply a rotation with this angle A0 or a rotation with this angle A1. Okay, so you can see here that A0 is by default 0 and A1 is by default pi over 2. Okay, but you can change that. And for Bob, I do the same, but with angles B0 and B1, which are set by default to pi over 4 and minus pi over 4. Okay, and then we measure. So what I'm doing here is defining another function that is going to run these circuits several different times in order to estimate the probability of winning. And here I also wanted to show you another different way of running circuits in the IBM quantum experience that is sometimes interesting. If you have several different circuits that you want to run one after the other, what you can do, of course, you can run one circuit, then run the other, but you can also stack all the circuits together in this list. Here I'm creating circuits for bits 0, 0, 0, 1, 1, 0, and 1, 1. And we pack these 4 circuits in the same experiment. And then we execute all the 4 circuits one after the other in the same job. So we do not have to wait for the queue 4 times, but just 1. And then we run this for the maximum number of shots, that is 8,192. Okay, so I forgot to run all these cells in order to obtain the result. Okay, so we create these circuits, and then what I'm going to do first is to run this on my on the simulator. Okay, let's see if it okay, it has finished, so I can run it on the simulator, and you see here that the probability of winning that we obtain is above this 85% that we were talking about. Okay, and what I'm going to do now is to run this on the actual quantum device. Again, I'm going to use the method that I showed you last week of selecting the least busy device. In this case, let's see what's it's selected, and then we will compute the probability of winning. Of course, we do not expect this to be perfectly 85% whatever, but it will be hopefully higher than 75%, and this will show that something random, something quantum is happening with these devices, and that in fact nature is not ruled by a local hidden variable theory, but by some quantum theory. Okay, so this probably is going to take a little bit. Let me check how many jobs. We have only 6 in front of this. Okay, so I don't know if there are questions while we wait for this. Let me check the chat. No? Okay, so let's move to a different protocol, a different topic. While we wait for this, we will go back. Okay. So I'm going back to the. Oh, it's finished. So let's see what is the result. So the result here is almost 82%. So this is not the 85% that we obtained with the simulator, but is much higher, significantly higher than the 75%. Okay, so this is somehow weak evidence that we are doing something quantum here. There are these loopholes that we are not addressing, but of course, I think this is very, very exciting because it's a very cool experiment. Okay, any question about this? Any doubt? Okay, I hope you also obtain similar results with your experiments. Okay, so let's go to the slides, and let's do something that is also very, very interesting and has a very cool name. Okay, this is another application of quantum entanglement, which is called quantum teleportation. Okay, so I know that there are some people here at CERN Open Lab that are hardcore Star Trek fans. So before they get very, very excited, I should say that this is not matter teleportation, but only information teleportation, which is something also very interesting, but we are not yet, or this cannot be used to teleport people from one of these ships to a planet and back, okay? But we are going to use this quantum entanglement at least to teleport information, okay? So the situation or the problem or the thing that we want to obtain or to achieve here is the possibility of Alice sending a qubit to Bob without a quantum channel. So if you remember last week when we talked about the BB884 protocol, Alice and Bob had a quantum channel and they could send qubits in different states over that channel, okay? But imagine that Alice wants to send a qubit to Bob and they do not have a quantum channel, okay? And the more general situation is when Alice has obtained this qubit from some experiment or from some other source, but she doesn't know what are the amplitudes of her qubit. Because if she knew, for instance, that the qubit is the plus state, she can call Bob on the phone and say, well, my qubit is plus, you can use a Hadamard gate and create your own qubit with the same information, okay? So here we are in the general situation in which Alice has a qubit. She has no information about this qubit, but either way, she wants to send it to Bob, okay? This might seem impossible. There is no quantum channel. Alice does not know the amplitudes or has no information on her qubit, but surprisingly enough, with the help again of entanglement, we can perform this sending information, sending this qubit from Alice to Bob, okay? So what is the protocol? I'm going to explain it first, and then we are going to see it, of course, in action. But the idea here is that we start again with an entangled pair. This is something that can be prepared in advance, as in the CHSH game. Alice and Bob can have some entangled pairs shared between them, just in case they want to send qubits to each other. Or another possibility is that there is a source of entangled pairs that can send to a part of the pair to both Alice and Bob. Okay, so this is like a source of entanglement that can on demand send qubits forming an entangled pair to Alice and Bob. Okay, what does Alice do? Alice has this qubit psi with amplitudes that we do not know, A and B, and she wants to send this qubit to Bob. So what she does is first she applies a CNOT gate to the qubit that she wants to send to Bob to teleport, and to her part of the Bell pair. Okay, so here the first qubit is the qubit that Alice wants to send. The second qubit is the part of the bell pair that Alice has. And the third qubit is the part of the bell pair that Bob has, okay? So she applies this C0 gate, and since the bell pair is in this state, you can very easily verify that now the situation is described by this state here. I'm working with 3 qubits at a time, something that we have not done before, but I think it's very easy to verify and to see what is happening, because we are applying gates to at most 2 qubits at a time, okay? So this is something that we know how to do. Then after applying the C0 gate, she applies the H gate. And this is again an exercise for you. You can just apply the H gate to the first qubit, to the qubit that Alice wants to send to Bob, and you will obtain this state here. I'm not going to give all the details because it's just a computation, but you can check this, and you should check this. This is the way of understanding what's going on. And then what is interesting is that you can factor the first 2 qubits to obtain the state in this form. Probably if you just apply the H gate, you obtain a bigger expression, but then you factor in this way. And notice that entangled with each possibility for the first 2 qubits, 0, 0, 0, 1, 1, 0, 1, 1, we have something that is similar to the qubit that Alice is trying to send to Bob. But it's not always exactly the same qubit. In the first case, it is exactly psi. It's A0 plus B1. And notice that this is what Bob has. This is what Bob has. The third qubit is the qubit that Bob has. So in the first case, this is exactly what Alice wants to send to Bob. In the second case, it's similar, but B and A are interchanged. In the third case, it's similar, but we have this relative phase of -1 here. And in the fourth case, we have a combination of these 2 cases. We have A and B swapped, and also the relative phase with the B, okay? But this is something that we can fix if Alice measures her 2 qubits, the first 2 qubits here in this state, making this collapse to one of these possibilities, okay? Because then she obtains, when she measures, either 0, 0, 0, 1, 1, 0, 1, 1, and she knows which of the 4 possibilities is the one that Bob has in that moment. And then what she can do is to communicate through a classical channel and send to Bob what are the results of her measurements. So she will send an email to Bob or call him on the phone and say, well, I have measured my 2 qubits and I have obtained, for instance, 0, 1 or 1, 0 or 0, 0 or 1, 1. With that information, notice that Bob now can reconstruct from the qubit he has and the information he has received the qubit that Alice wanted to send to him. Because if Alice measures 0, 0, he does not need to make any transformation. If Alice measures 0, 1, he has to apply an X gate, because the X gate is going to interchange the A and B. If Alice measures 1, 0, then Bob has to apply the set gate, because if this set gate is going to introduce another minus here, which will cancel with the minus that we already have. And if Alice measures 1, 1, what Bob needs to do is first to apply the X gate and then apply the set gate, okay? And this is exactly what we are doing here with this circuit. So this is the creation of the bell pair, okay? This is the qubit that Alice wants to send to Bob. This is the part of the bell pair that belongs to Alice. This is the part of the bell pair that belongs to Bob. So here, this is the bell pair being created. Now, Alice applies the C0 and the H, and she measures. And then with this information that is sent over the classical communication channel, Bob knows whether he has to apply the X gate or not, depending on the second qubit or the second result that Alice obtained in her second qubit, and whether he has to apply the Z result, the Z gate. Okay, and with this he reconstructs the qubit that Alice wanted to send to him. Okay, so some comments are in order. Of course, you need to, or you should, in order to understand all the details, do these computations. They are very easy, and they will give you a feel of what is happening there. But some comments are in order to understand completely the philosophy and the implications of what we are doing here. As I've mentioned before, this is not matter teleportation. This is just information that we are teleporting. In fact, whatever the implementation of the qubits that we are using, photons or trapped ions or whatever, Alice and Bob will still have their own photons or their own qubits, okay? But the information has been teleported, okay? Another thing that that is very important to notice is that when Alice measures her qubits, in particular the qubit that she is trying to teleport to Bob, she loses completely this qubit. Okay, now she only has the result of the measurements because the qubits have collapsed to whatever she has measured. If this were not the case, then we would be contradicting the no cloning theorem, because if Alice still had her initial qubit with this circuit, we would be creating copies of the same qubit, and we know that this is not possible. Okay. Another thing that is interesting is that, well, we cannot send a qubit only by giving two classical bits. It's impossible. There is not enough information in 2 bits to specify completely a qubit. But if we also have what is sometimes called an E bit, an entangled bit, that we can use for this protocol, then 2 bits plus 1 entangled bit are sufficient to send 1 qubit. And this is sometimes expressed with this kind of inequality here. And we will see a different related inequality in a few minutes. Okay, so this is another way of measuring the resources that we need for some quantum communication protocols. We have qubits, we have bits, and we have classical bits, and we have entangled bits. And there are several relationships between them, what we can communicate if we have some of these resources, and what we need if we want to send or to communicate several other of these resources to other people. Okay. Another thing that is very important, especially since there are many physicists in the audience, is that this teleportation is not instantaneous. Okay, it may seem so because somehow you might think that when Alice measures her qubits, that qubit is already in the possession of Bob. But notice that Bob does not know until Alice sends the information of the results of her measurements, whether he is in this situation or in this other situation or in this other situation or in this fourth situation. And the qubit is completely different, and in fact he has to do different transformations to recover the original qubit. Imagine, for instance, that the qubit that Alice wants to send is a 0. Okay, then Alice measures and makes the system collapse to one of the possibilities, but Bob in that moment has either 0 or 1, because if he is in this situation, then A was completely 1 because Alice had a 0 at the beginning, and then Bob has a 1, okay, until Alice tells him that she measures 0, 1, he cannot apply the correct gate in order to recover the correct qubit. Okay, so the teleportation is not instantaneous. If Alice does not send the information about the measurements, Bob has no way of recovering the correct state for the qubit. And this has to do with what is called the no communication theorem. There is sometimes this confusion that entanglement can be used to instantaneously send information. Even some science fiction novels and movies and series use this. Oh, we have this entanglement, then we have faster than light communication. This is not the case. It can be proved. It's not very difficult, but you need these concepts of density matrices that we have talked about sometimes in the past. In order to prove that whatever Alice does to his part of the qubit of the entangled pair is not enough for Bob to receive information. Okay, and this is called the no communication theorem, and of course, it is not violated with this teleportation protocol. Again, this is something as in the BB884 protocol or in the CHSH game that has been used in practice and has been shown experimentally that you can teleport this information. And the current record is over 1,000 kilometers from Alice to Bob, from the receiver to the sender. Okay, this was achieved by some researchers in China with the help of satellites, and they were able to teleport information from qubits in the atmosphere to the ground. Okay, and I'm going to show you. There is a question, but it's a little bit long. I will try to address it later. Okay, I'm going to show you this in the. Oh, I lost my screen. Sorry. I'm going to show you this in Queer. You can click this link here to go to this circuit in which I have prepared the quantum teleportation protocol. You see here that, well, this H might better be here to see that this is creating the bell pair. This is the part in which Alice does these operations and measures, and then this is the correction that Bob has to apply. And this is the qubit that Alice is sending. I have used here a rotation to make this qubit change in real time. And you see here that what Bob is receiving is exactly the same.
Sorry, we are not able to see the screen, I think.
Okay, sorry. Why?
Okay, now we can. Perfect. Thank you.
Yeah, but this is not this one. Sorry. I messed up. It's not that one, is this one. Okay? Now you can see it. Sorry. I had two Queer windows and I selected the incorrect one. Now you can see the teleportation circuit. Yes? Okay. Okay, so I will repeat. Here, this is the part in which the bell pair is prepared. This is the part in which Alice measures his part of the qubit. And then this is the correction that Bob has to perform in order to obtain the same qubit that Alice had. So here, I have applied a rotation in order to make this qubit change, evolve over time. And you see that what Bob is receiving is exactly the same. If you change this rotation for next rotation, for instance, of course, it will also work. Okay? Okay, so let me go back to the slides. Okay. Let me try to read the question quickly and answer it. Okay, so I will read it to you. This is a question by Matteo Paltenghi. I hope I have said it correctly. It's a question about the slide 69. You said that we are not breaking the no-cloning theorem with this result. My idea is the following. With the teleportation, besides the teleporting of the qubit, we are also able to get a measurement of that qubit. That is lost, but still we have a measurement. If we chain n blocks of teleportation circuits, we can teleport the qubit n times. If we do that a great enough number of times, we can get the average number of times it collapses to 0 and to 1 without having corrupted the qubit, because Bob receives it. In these ways, we were able to inspect the qubit without destroying it. Is it correct? Well, this is an interesting idea, but notice that here, when we measure the first two qubits, the probability of obtaining 0, 0, 0, 1, 1, 0, 1, 1 does not depend on A or B. It's always 1/4. So you will obtain 0, 0, 0, 1, 1, 0, 1, 1, each 25% of the time, independently of B and A. Okay? So you, although you do this and you obtain measurements, of course, you obtain 0, 0, 0, 1, or whatever, this is completely uncorrelated to the values of psi. Okay, so you do not obtain any information about the values of the qubit that you are teleporting. Okay, so it's a nice idea, and this is something that I really encourage you to do, to try to manipulate or to change the protocols to see if you can find a problem with them or a way of doing it in a different way, because this is the way in which you understand these questions. For instance, something that you can do now that we have studied entanglement is to try to see what would happen in the BB884 protocol if when she intercepts the qubit that Alice is sending to Bob, entangles that qubit with one of her own, and then waits until Alice and Bob start sharing information about the bases that were used for the encoding and all that. Okay, let's see try to see if that gives some kind of advantage to Eve, or, and this is a hint about the result you should obtain, or if Alice and Bob can notice that something is going on with the qubits that they are using. Okay, so this is something that is very, very interesting, and I encourage you to do, to try to manipulate and to see different scenarios and different ways of doing these protocols in order to understand what is going on, what works, what doesn't work, and what are the limits of these protocols that we are studying. Okay, so thank you very much for the questions. This is always very, very interesting. Okay, so I don't want to spend too much time on this, but there are other ways of using this quantum teleportation protocol that are also very interesting. For instance, there is this protocol that is called entanglement swapping, that allows us to create entanglement between qubits that have never been in contact to each other. Okay, so far we know that we can create entanglement if we have something like a CNOT gate, some physical operation. If you check these books and these resources that I mentioned at the beginning of the lecture, you will see possibilities of implementing this physically. But imagine that you have an implementation with a CNOT gate, then you can create entanglement between qubits. But this is something that you are applying to these two qubits that are normally close to each other, and this is a joint operation that you do on these qubits. With this idea of quantum teleportation and a nice twist that we are going to use here, we can entangle qubits that are not closed, that have never been closed. Okay, what is the idea? Well, so we have Alice, we have Bob, and we have again Charlie. Okay, and Alice and Bob share an entangled pair, and Alice and Charlie also share an entangled pair. Okay, and what we want at the end is Bob and Charlie sharing an entangled pair. Okay, but there is no quantum channel between them. There is no way of obtaining sending qubits from one to the other. Okay, so in this case, what we are going to do, I will explain it very rapidly, is that, well, Alice and Bob, well, I will explain what are the meaning of the different qubits. The first one is, the first two are the qubit, the entangled pair that Alice and Bob share. So the top one belongs to Alice, the second one belongs to Bob, and then the bottom two qubits are the other entangled pair that Alice and Charlie share. So the bottom qubit also belongs to Alice, and this qubit above it is the one that belongs to Charlie. Okay, so you see here that Alice and Bob are sharing an entangled pair. Alice and Charlie are sharing another entangled pair. And now what we do is that Alice uses the quantum teleportation protocol to send the part of the entangled pair that she shares with Bob to Charlie. Okay, so you see here that she's doing the entanglement protocol between this qubit that she has, this other qubit that she has, and she sends the information to Charlie so he can correct his qubit. Okay, and you can check, in fact, if you click here, I will do it in a minute, you can see it in Quirk, that now what has happened is that Alice has effectively sent her qubit, the part of the entangled pair that she was sharing with Bob, to Charlie. Okay, but this qubit was entangled with the one that Bob had. So now this third qubit, which the first qubit was teleported to the third, the first one was entangled with the second, now the third and the second are entangled. Okay, so this is a way of sending or swapping the entanglement that Alice and Charlie were sharing, and now this entanglement is shared by Charlie and Bob. Okay, let me open this and let me share the screen with you. So I have many windows now here. Let's see if it is this one. Okay, you should be seeing, no, I think this is not the one, this one, sorry. Okay, so now you should be seeing the screen here with Quirk. You see this is the circuit that we were using, and I have included here a visualization of the amplitudes. This is the qubit that Bob has, this is the qubit that Charlie has, and you can see that the joint state of these qubits is an entangled state, a Bell pair. Okay, and this has been obtained without any communication between Bob and Charlie. Okay, another thing that you can do with this quantum teleportation protocol is also very interesting, is what is called gate teleportation. Okay, so the idea of gate teleportation is to not teleport just a qubit, but teleport a qubit and apply to it a certain gate. Okay, so the circuit is this one here, which is very easy to understand, because if you see, we are applying to the third qubit a gate U, which is the one that we want to teleport, the inverse of that gate. So in fact, these two gates cancel each other, okay? And then we have a U here. So if you cancel this U with its inverse U dagger, you only have a difference with the teleportation circuit, which is the application of this U here. So of course, what you are doing here is, if you cancel this, you are teleporting psi to the third qubit and then applying U, okay? So at the end here, you have U applied to psi, because up to this point, you teleported psi, and then you applied the gate U. So how is this useful? Because it seems that, well, we are teleporting and then we are applying U. The importance of this kind of protocol is that we group the operations in a certain way, okay? So instead of just preparing an entangled pair here, we prepare this pair in which, in addition to entangling the two qubits, we apply the U gate, okay? And sometimes this is easier than just applying the U gate to a general qubit, okay? So there are situations in which you can do this in an easier way than applying U or implementing U in a general form, because you only need to apply it to states of this kind. So this is a particular case. And then there are situations in which applying these four gates, all one after the other, the different combinations that you have here, because X and Z can be applied or not, but sometimes applying these gates is easier than applying a general U gate, okay? So if these two conditions are met, if preparing this kind of a state and applying this combination of gates is easier than applying U to a general qubit, then this is useful, okay? Because then you can apply U to a general qubit by doing some things, these two things, this preparation and this application, which are easier. This may seem a little bit convoluted, a little bit strange, but this is something that happens, for instance, when we are doing what is called quantum fault-tolerant computation. So in that context, what we are doing, we will see some of these concepts in the last lecture, is using several qubits to encode the information of a logical qubit, and then we apply gates, which are the analogous of the gates that we know, okay? In that situation, for instance, the T gate, which is very important, we will see that in a few slides, cannot be applied easily, because we are working with not physical qubits, but logical qubits. And with that error correcting codes that we need to use, it is not easy to apply the T gate. What we can do is to create these entangled states with the application of the T gate, and then applying these gates here, it's easier than applying T. Okay, so this is something that is useful. We will see it in the context of fault-tolerant quantum computing. Okay, just as some some protocol in which we can apply these ideas of quantum teleportation. Okay, so finally, to end up with these quantum teleportation ideas or quantum communication ideas, I want to show you another protocol, which is somehow the inverse of the quantum teleportation protocol. In the quantum teleportation protocol, Alice and Bob shared an entangled pair, and then they used 2 bits to communicate a quantum bit, okay? And this is something that we wrote as 2 bits plus 1 entangled bit is worth at least as much as 1 qubit, okay? Now what we are doing is to use 1 qubit and 1 entangled bit to communicate 2 classical bits. So somehow this is a reverse of the protocol of quantum teleportation. This is interesting because in general, if you send just 1 qubit, the other person, if Alice sends to Bob just 1 qubit, Bob can only obtain 1 bit of information from the qubit. This is a little bit trickier than it seems to prove, but the idea is simple. This is called the Holebos bound, and the idea is simple. If you receive a qubit, you can move it around, but eventually you have to measure it in order to obtain information from it. And when you measure the qubit, you obtain a 0 or a 1. You obtain just 1 bit, okay? But if Alice and Bob share in advance a Bell pair, then they can use the sending of just 1 qubit to communicate 2 bits, which is double the information that you can send with just 1 qubit, okay? How to do this? Well, the protocol is very easy. The idea is that initially, as in all the other protocols that we have been studying today, Alice and Bob share a Bell pair, an entangled pair, okay? And now, after some time, this can be done in advance, after some time, Alice wants to send to Bob 2 classical bits, 0, 1, 1, 0, 1, 1, 0, 0, whatever, okay? And then, if the second bit that she wants to send is 1, she applies X, the gate X, to the part of the entangled state that she possesses. And if the first qubit, the first bit that she wants to send is 1, she applies the set gate to her qubit, okay, in that order. So in the circuit, we can see this protocol. This is the creation of the entangled pair. And later, when Alice wants to send something to Bob, she uses this B2 and B1 to apply or not the X and Z gates. And then she sends her qubit to Bob. So now Bob has both parts of the entangled bit. And what Bob does is to apply a CNOT gate, apply an H gate, and then he measures his qubits, and what he obtains is exactly the 2 bits that Alice wanted to send, okay? Let me show you this with an example, and as an exercise, you can try the other 3 examples. So here, what I'm going to show you is the case in which Alice wants to send 1, 1, and what are the different states that the qubits are in the different parts of the protocol. So we start with this entangled pair, with this Bell state, and then Alice needs, remember, to apply first the X gate and then the Z gate, okay? So what she obtains is exactly, she applies this to the first qubit, okay? So what she obtains is exactly this state here. You can check this, okay? But now Bob applies C0 and he obtains this state here, okay? Again, this is something that you can check very easily because there is only one operation that you need to apply here, okay? And then notice that he has to apply an additional H gate, but this part here is the minus state. So when he applies the H gate to the minus state, he obtains 1, 1. And when he measures, he recovers exactly what Alice wanted to send to him. Okay, and in the other cases, it's similar. You can check that this works. And if you want to have a deeper intuition of what is going on here, let me go back to the slide in which we talked about the Bell states, okay? So what we are doing here, in fact, with this super dense coding protocol is we start with this entangled state, and with the edge, with the X and Z gates, we move to one of these other four states here, okay? So at the end, Bob is going to have one of these different states which are orthogonal to each other, okay? So what we are doing here is to encode 2 bits as 4 different states which are orthogonal to each other. And when states are orthogonal, we can use measurements to distinguish perfectly among them, okay? So when we distinguish among these 4 states, we obtain the 2 bits that Alice wanted to send. Okay, so let me go back to the example here and to the circuit, and we are going to run this. We are going to run this on the IBM Quantum Experience. So let me see if I can share the correct screen now. It should be where? Okay. I have too many open. Yeah, I think it should be this one. Yes. Let me close Quirk. Okay, and we are back in the IBM Quantum Experience. And you can find in the Indico page for the lecture this new oh, we didn't run the CHSH notebook, so we are going to run both at this. Oh yeah, yes, we obtained the results. Yes, sorry. So we are going to run this protocol, this notebook for the quantum teleportation and the super dense coding. Okay. So this is something that should be quite simple to understand now, but I'm going to introduce some new operations that you can do in Qiskit that sometimes are useful. So what I'm going to do first is to implement the quantum teleportation. And what I'm doing here is to create randomly a state for the qubit that Alice wants to send to Bob, okay? What I'm doing is to generate real numbers between -1 and 1, and then I normalize to obtain a correct set of amplitudes for the qubit psi that Alice is going to send to Bob, or teleport to Bob, okay? Something that we had not done before, if I remember correctly, is to give names to the different sets of qubits or the different registers in our circuits. And this is something that sometimes is very useful because, well, when we have 1 or 2 qubits, it's very easy to remember what each qubit is doing. But when we have many qubits, some parts of the circuit are computing something, other parts are computing a different thing. So it's useful to give them names, like variable names, so to say, in order to see what is going on. Okay, so here I'm going to call psi the qubit that Alice wants to teleport to Bob. I'm going to call Bell the 2 qubits that form the entangled pair, and then we have this classical register for the measurements that I'm going to call just C, okay? And then what I'm going to do is to create with these registers, I'm going to create a quantum circuit. So this is a way that is different to create a quantum circuit to the ones that we were using before. Before we were just specifying the number of quantum bits, the number of classical bits. Here we are creating in advance the registers, and then we are creating a circuit by joining those registers, okay? And this is also an interesting operation that we had not seen before, which is the direct initialization of the state of a qubit with some values, in this case, the C1 and C2 that we have created at random before, okay? Notice that this is something that you cannot do in general with a quantum computer, okay? You cannot just choose the amplitudes for your qubit and do it like that, okay? You need to apply some gates. But here we are working with the simulator, so what happens is that we access the values of the simulator and we set the amplitudes to that. In a quantum computer, this should be translated to gates that create that state, okay? So it shouldn't, it wouldn't be like just one instruction, but probably a couple of gates or whatever, depending on the architecture, that sets the amplitudes to the correct values, okay? So in this case, you see that this is the qubit that has been created, okay? This is the one that we are going to teleport. So now what we do is, with this first part, we create the Bell pair. I'm including here these operations, which are not really operations or gates, are just separations, barriers, in order to see the different parts of the circuit when we draw it, okay? So this first part is the creation of the entangled pair. This part here is the operations that that Alice needs to do, the C naught, the H, and then the measurement. And these are the parts, the operations that Bob needs to do in order to recover the correct qubit that is being teleported. Okay, so if we draw this, here we see the gate that should be translated into several gates that creates the state that we want to teleport, then the creation of the entangled pair, then the operations by Alice, and then the operations by Bob. This gate here may seem strange, but this is the way in which sometimes the control set is represented. Okay, so here is a set controlled by the first qubit. Okay, and I'm going to run this on the state vector simulator. And well, in this case, I don't know what is going to be the result of this. So I'm going to use the whole state of the 3 qubits. And for some values of the first 2 qubits, we will obtain for either 00, 01, 1011, the correct amplitudes in the rest of the state. Okay, so here you see that we had 0.0998. It's exactly what we have here. 0.794. Well, the same here up to rounding, and also for the second part of the state. Okay, so this you can repeat several times and you will always obtain the correct answer. Regarding superdense coding, this is also very easy. I'm going to create just one register, which I call Bell, then a classical register for measuring the results at the end for Bob. And then I'm going to first Bell pair, okay? This is the initial part, the sharing of the entangled pair. Then I'm going to generate for this 2 bits that she wants to send. And depending on those bits, Alice is going to apply the gates X and Z. In this case, she's sending 1, 1, so she has to apply both gates. Now, this qubit is sent to Bob, that now possesses both parts of the entangled pair. He can apply the C naught, the H, and then measure the result. And if we execute this circuit, of course, Bob receives 1. Okay, you can repeat this several times and you will obtain always the correct result. Okay, let me go back to my slides. Okay, any question up to this point? Any comment? Okay, so we have time to cover one last section, which is exactly this time what I was aiming for. Okay, so we are on time, which is a little bit different. Okay, so just to recap a little, up to this point, we have studied mainly quantum communication protocols. We have studied BB884, which can be used for quantum cryptography. We have studied today quantum teleportation, quantum superdense coding, also the CHSH game. But none of these protocols can be considered properly computations in the sense of having some initial data, some input, doing some operation and obtaining a result. Okay, we are sending information, we are being able to share a key for then using it in a protocol of classical cryptography or whatever, but we are not doing computation. We are not really running algorithms with input data and obtaining output data. Okay, this is something that we are going to start to do now until the end of the course. And for that, we need to introduce a new element. Up to this point, we were using superposition and the uncertainty principle, for instance, for the security of the BB84 protocol. So we use superposition a lot there. Then we used entanglement. Today was all about entanglement. The CHSH game and these two protocols were exploiting entanglement to do some interesting communication tasks. But there is a third ingredient that we need in order to exploit the full capacities of quantum computers for quantum computation, for quantum algorithms, and this is interference. So far we know about superposition, about entanglement. Now we are going to use interference to do some computations, some to execute some algorithms in a faster or better way than with quantum, with classical computers. Okay, so we are going to study today the first ever quantum algorithm, which is called Deutsch's algorithm, which was proposed by David Deutsch in 1985. This is a little bit a strange problem that we are going to solve. This is not practical in any sense, but was the first hint that quantum computing, quantum computers could do things in a faster way than classical computers. Okay, so you will see that this problem is really not practical, but it's something that quantum computers can do in a faster way than classical computers. And next week we are going to extend this with what is called the Deutsch-Jotz algorithm, which is a generalization of this problem to a situation with a lot of qubits. Here we are going to work with only 2 qubits, but then we are going to work with a lot of qubits. Okay, and the statement of the problem is a little bit strange, as I was telling you. So the idea here is that we are given a Boolean function, a 1-bit Boolean function, which is implemented with a quantum circuit. Okay, we have already talked about the possibility, and we will revisit this topic again next week, about the possibility of implementing classical operations with quantum computers. This is something that we can always do. So we are given here a quantum circuit that implements a Boolean function. Okay, and since this is a Boolean function with 1 input and 1 output, it can only be one of 4 possibilities. It is either always 0 for all inputs, always 1 for all inputs. It's either the identity, it returns 0 when the input is 0, 1 when the input is 1, or it's the negation. It returns 1 when the input is 0 and 0 when the input is 1. These are the four possibilities, okay? So we are given one of these in a quantum circuit, but this is a black box. This is a circuit that we can use, but we do not know what gates are inside the circuit, okay? We can plug this circuit in our quantum computer and use it together with other gates, but imagine that we cannot see inside. This is something similar to what could happen if you are doing classical programming and you receive some function which is already compiled, and you can call it, you can use it, but unless you reverse engineer what is inside the function, you don't know what it's doing. Okay, so this is something that you can call. You can put call it as many times as you wish, with as many inputs as you wish, but you can not see what is inside it. Okay, and the problem that we are asked to solve is to determine whether the function that we have been given is either constant or balanced. So constant is if it always returns the same value for all the possible inputs, always 0, always 1. Yeah, and balance is if it returns half of the time 0, half of the times 1. Okay, so obviously this covers all the 4 different cases for functions, Boolean functions of 1. Okay, and in the classical setting, if we are given a black box implementing this function, we are allowed to use it, and we need to determine whether it is constant or balanced. It is clear that we need to call the function 2 times. Okay, we need to call the function with 0, and we need to call the function with 1 and see the answers and see if they agree or disagree. If they agree, then the function is constant. If they disagree, the function is balanced. And there is no way around this, because if we just evaluate the function on one value, say in 1, and it returns 0, we have no information about whether it is constant or not, because for the other input, for 0, it can be the same or it can be different. Okay. Amazingly enough, in the case of quantum computing, we can solve this problem with just one call to this oracle, with just one evaluation of the function. But we need to do this in superposition, okay? And we are going to use the superposition at the beginning, then the entanglement, and at the end, interference, okay? First, in order to understand the algorithm, we need to explore a little bit more this concept of an oracle and how we can use it in our quantum circuit. So remember that all the operations in a quantum computer, except in the measurement, are reversible. Okay, so all gates are reversible. So this black box that we are given must also be reversible. Okay, so the way in which we can access the values of this function f, and at the same time keeping the reversibility of the operation, is by using this oracle, which has one input x, which is the value on which we want to evaluate the function. Okay, and this is not going to change when we use the oracle for the function. And then another quantum bit, which is used to obtain or to recover the value of the function on x. Okay, and in order to make this reversible, notice that I'm using here the XOR operation, because if I apply again this oracle after this first application, I will have y XOR fx XOR fx, and the two fx will cancel, and I will return to xy. Okay, so this is reversible because in fact it is its own inverse. Okay, so we have this way of implementing the action of a Boolean function in this reversible way, and this is something that can be done with any Boolean function just by using the gates that we have been studying. Okay, we will talk a little bit more about this when we have oracles for a bigger number of qubits. Okay, so we are given this oracle that acts on this way and always gives us this evaluation of f on the input x. If we set y to 0, then we have here the result of f on x, and we can use that in our subsequent computation. Okay, we are given this oracle. How do we use this oracle? Just one time in order to answer the question that is posed in Deutsch problem. Well, the idea is to use this very simple circuit here, in which notice that we are starting with qubits 0 and 1. Okay, so this is different to what we usually do, but this is something that is not difficult, because we can start with 0 and then apply an x. This is something that is easily done, so I can just put 1 here and notice that this is not different from the general situation. Then we apply these H Hadamard gates, then the oracle, and then another Hadamard gate and a measurement. Okay, I will explain the behavior of this circuit in a minute with all the states, but notice that this is extremely simple. These are in fact very simple gates: the X gate, the H gate, and then this measurement, and of course the oracle that we are given. Okay, and surprisingly enough, this circuit gives us the correct answer to the problem of whether f is constant or is balanced. When we observe the result of this measurement, if we obtain 0, then the function implemented by the oracle is constant, and if we obtain 1, this means that the function implemented by the oracle is balanced. Okay, but notice that I have used only once the oracle. I have called to this oracle only once, and this is something that in the classical setting we cannot do. With just one call, it is impossible to obtain this global information about the function, because this is in fact information about the whole operation of the function. And with just one call, in the classical case, we only obtain information about what happens with one of them. Okay, why does this work? Okay, so I'm going to show you here the computation. Again, this is something that I encourage you to try on your own, to follow all the steps. This is something that at the beginning seems a little bit strange, seems a little bit like magic, because we are doing here some computations that are not easy to understand intuitively. It's not something that is similar to a classical algorithm in any way. But we will see that at the end it gives the correct answer. Okay, so it's interesting to check all the steps and try to see what is happening here. At the end, I'm going to give you some intuition of what is happening here in with a physical analogy. Okay, but I encourage you to try and check all these computations and try to feel why this is working. Okay, so here is the circuit. Remember that we start with the initial state 0, 1, and then we apply these gates H to each of the qubits. Okay, so these are applied independently. In fact, this is a tensor product of the gates. So we apply H to 0, H to 1. If we apply H to 0, we obtain the plus state. If we apply H to 1, we obtain the minus state. Okay, and we can write this in this other different way. Okay, if we just multiply here, we obtain this other different expression for the same state. Now we apply the oracle, but remember what was the operation of the oracle. The operation of the oracle was just adding f of the first qubit to the second qubit. Okay, so by linearity, we can operate first on this part of the state, then on this part of the state, and just add both parts after the operation. Okay, If we apply here again linearity, we can operate first with 0, 0, and then with 0, 1, and then we have to subtract these two results, okay? So if we apply to 0, 0, what is going to happen is that the oracle is going to add the f of the first value to the second qubit, okay? In this case, the second qubit was 1, so it's going to add the f of the first qubit, which is 0, to the second value. And for the second part is the same, but now the first qubit is 1. Okay? So you would agree with me that this is the state after we have applied this oracle here. But we want to manipulate this state a little bit more in order to obtain something that is easier to work with before we apply the Hadamard, the final Hadamard gate, and then the measurement. Okay, so notice that if the Boolean function on 0 returns 0, then this f0 is 0, it's nothing. So we have exactly what we had at the beginning, 0 minus 1. However, if f of 0 is 1, then this is 1, this is 1, 0 plus 1 is 1, 1 plus 1 is 0, and we obtain 1 minus 0, which is, of course, minus 0 minus 1, okay? And you can say, well, but that is exactly the same state, because you told us several different times that a global phase does not affect the state of the qubit, okay? But notice that in this case, we have two different parts. And the same can happen, the same that happens for F0 happens for F1. So in the first part, we are applying F0. In the second part, we are applying F1. And we can have a difference in phase in the two parts. We can have not a global phase, but a relative phase, okay? So in fact, I can write this operation here as minus 1 to the power f of 0, because if f of 0 is 0, this is 1. And if f of 0 is 1, this is minus 1, okay? And this is a way of writing both possibilities with just one term, okay? And the same is true for f of 1. We can write the second part as minus 1 to the power f of 1 times the state 0 minus 1. Okay? So these are just algebraic manipulations. Let's do one additional manipulation. The additional manipulation is to multiply all the state, and now this is indeed a global phase because I'm multiplying all the state by minus 1 to f to the power f0, okay? And if I multiply all the state, not just part, but all the state by this global phase, what I obtain is exactly the same, okay? But if I multiply the state by minus 1 to the power f0, these powers here cancel, because then I have minus 1 to 2 times f0, which is always 1. And here I have minus 1 f0 plus f1. And here you can begin to see that now we have some information about the global behavior of the function, okay? This is something that we wanted in order to know whether the function was constant or balanced. And in fact, if both values are the same, then this is the case in which a function is constant. What we have here is again 1. So we will have 0 plus 1 times 0 minus 1. Okay? So it's important to notice that here I have 0 plus 1. However, if f0 and f1 are different, one of them is 0 and the other one is 1. So their addition is 1. And this is minus 1. So instead of 0 plus 1, in the first qubit, I'm going to have 0 minus 1. Okay? But now the final step is to apply the H gate. And when we apply the hk to 0 plus 1, we obtain 0. And when we apply the hk to 0 minus 1, we obtain 1. And that is exactly what we measure at the end of the circuit. So if the function is constant, we are going to measure 0. If the function is balanced, if the function is not constant, we are going to measure 1. Okay? And we have done this, we have solved this problem with only one evaluation of the function f. Okay? So this is, as I told you, a little bit like magic, because we have done some strange manipulations of symbols here, and at the end we obtain the result with only one call. How to try to interpret this in a more intuitive way? Okay, so notice that the whole role of this second qubit is what we have here, to introduce this relative phase, okay, which can be 1 or minus 1, okay? But it's never transformed. So in fact, what we are doing is an operation which either adds a phase of 1 to the first qubit, or a phase of minus 1 to the first qubit. This is similar to physical experiments, quantum mechanics, like the double slit experiment, or the one that I'm showing you here, which is called the Mach-Zehnder interferometer, which the physicists in the audience surely will know, in which we have an arrangement with photons. We have a beam splitter that divides the photons somehow, the photons that arrive, half of them in one direction, half of them in one direction. But really what is happening is that we have a superposition of both paths. So this acts exactly or similarly to the H-gate that we are using. And then in one of the paths, we add a phase. We add some device that changes the phase of the photons that go through that direction. And then when we recombine the paths of the light, again with a beam splitter, or in our case with something similar to a H-gate, we obtain the probability of measuring in this direction and in that direction, which is depending on the angle that of the phase that we have introduced. Okay, so this is exactly what is happening with the Deutsch-Jozsa problem. Sometimes we are adding in both paths the same phase when the function is constant. Sometimes we are adding a minus phase in one path and no phase in the other. And this causes the interference at the end, and this causes that we measure different values depending on whether the function is constant or not. Okay? So this is all that I wanted to tell you. Thank you for today. Oh, somebody's telling me that I missed an H in Mach-Zehnder. I will correct it, sorry. So thank you very much for your attention. I will be happy to answer questions by email, and I hope to see you again next week. Thank you so much.